Okay, so welcome everyone to our VMOL seminar for today. So our guest speaker today is Reza Shahneh, and we've heard from Reza before, but we're very excited to hear him tell us a bit more about High-Throughput ModiFinder. Just a brief background. Reza is currently a PhD student in Ming Wang's bioinformatics lab at UC Riverside. Before that, he obtained his master's also at UC Riverside. And then before that, he was an undergrad at Sharif University, which is in Tehran. So we're very excited to have you, Reza. And with that brief introduction, yeah, the floor is yours. So, yeah.
Okay, thank you for the introduction. Yeah, so today I'm going to talk about the high-throughput ModiFinder. So I have talked about the ModiFinder and what it does before. Today, it's like it's going more in depth through the ModiFinder, especially a high-throughput workflow that we made, hopefully helping discover new products and annotating it. So just so that everyone's on board, I'm going to go through the basics of ModiFinder again, and then after that, I'm going to talk about the new workflow that we made. So what we have at the moment is that I'm sorry. Oh, yeah, I've mistakenly removed one of my slides. I'm sorry. So the problem that we have at the moment is that in like an overview of the problem is that we want to identify small molecules from their mass spectrometry. And that, of course, is a hard problem. Even though mass spectrometry does have a lot of information and it's a very powerful technique, it still does not have these informations very easily available to us. And on average, 87% of all the MSMS data gathered so far is an unknown entity. So we're going to try and handle this issue as far as we can with the ModiFinder. So the basics of that is that, so we know that molecules don't appear in isolation in nature. This is also the basis of works such as the molecular networking. And using this, we are going to create a tool that tries to find the modification site from a known compound, and using that, we are going to be able to annotate an unknown analog of that known compound. And this is not a new approach. This has been used in metabolomics. I'm sorry, this has been used in proteomics before. And the basics of that is that we're going to look at the shifted peaks, and those shifted peaks, they contain information about the modifications that happened in the analog. So, of course, I'm going to go in more depth, but the problem setup is that we have MSMS of a known structure and also the MSMS of the unknown compound, the unknown analog, and also we have the structure of the known compound. And using these inputs, so basically the three inputs that we have, the two MSMS data and the one structure, we are going to try and find the modification site on that known compound. Okay, so what's the intuition behind ModiFinder? So here, assume that we have two compounds. I've illustrated it with a toy example using these like puzzle pieces. So we can see that the compound 2 has one modification as a red puzzle piece. And on the right, you can see the MSMS data. So once we align this MSMS data, we see that there are peaks that are not shifted and exist in both of them, but also there are peaks that have shifted the same mass as the red puzzle piece. Once we start annotating these peaks, then the shifted peaks, they must have contained this new added part. So here, for example, we have figured that the red peak was corresponding to the green puzzle piece. And now that we see on the new compounds MSMS, it has been shifted with the same mass as the red puzzle piece. So we're assuming that this new peak must contain both red and the green puzzle piece. So similar fragments, they have the same weight, they have the same substructure annotated to them, and the shifted ones have the modification. So here's an example for this. That you can see the known molecule, the modified analog, and I have highlighted the modification part in red. So there are fragments that have the same weight and they are corresponding to the same part of the molecules. And also there are fragments that differ by that delta, the additional part, and that is corresponding to a shift. I'm sorry, this highlight is not the correct highlight. I don't know what happened to the slide. But anyway, the idea is that we are going to find the peaks that have shifted the same amount as the difference in the precursor masses. And using that, we are going to find, trying to find the modification site. So here, for example, the blue highlighted part corresponds to a substructure that we know have shifted with the same mass as the modification, and green is also another example of such substructure. And then the intersection of these two, we theorize that is should be the modification site. So the way we do that is that the first step, we're going to find the annotations for the peaks. And we do that using in silico fragmentation tools. So we start by, this is a very similar algorithm as to the magma algorithm. We start with the whole molecule, and then in each step, we remove one of the atoms and we calculate the theoretical mass of the remaining substructures and see which peaks they can be assigned to. So for example, we start by atom A, we remove that, and then the remaining substructure, we measure the weight, assign to whatever remains. Then we go to the atom E, we remove that, and this process continues. And this way, we obtain different substructures in the molecule graph, and then we measure the weight of these substructures, and we assign that to the peaks. So for example, once we do that for this example molecule, we end up with these annotations to the peaks. And of course, you can see that one peak can be annotated with multiple different substructures as they all have the same weight. So the issue with this was that it was too general and ambiguous. Usually, most of the peaks, they were annotated with too many substructures, and at the end, there was no intersection of these shifted substructures that we could work on. They essentially covered the whole molecule. So the first improvement we did over that was to use the formula that was contained from the series. So we ran series on the data, and for the peaks, we captured the formula assigned to that peak, and then we filtered the substructure annotations to the peaks using this formula. For example, here, we figured that for this specific highlighted red peak, the formula should be this, and therefore one of the substructures were removed. The second refinement we did was to use helper compounds. So as I mentioned before, molecules don't appear in isolation. They are usually part of a network of compounds. And here we are using the same concept I described for finding the modification site, but over two known molecules. So here we have our known compound on the top, and assuming there is one other known compound in the network that is substructure or superstructure of the known compound. We call those compounds helper compounds. Here we can see that the known compound is a substructure of that, but it could be the other way around. That doesn't change the way this part of refinement is done. So in this part, these helper compounds and the known compounds both are known. So we have their MSMS data and their structure. So after the annotation, we can see exactly where the modification happened. And based on that, we can filter the potential substructure annotations to the peaks. For this specific example, you can see that the second peak in the top was annotated with the combination of yellow and blue puzzle piece, but also this orange corner puzzle piece. However, this orange corner puzzle piece is not attached to the red puzzle piece. And therefore, when we look at this, the alignment, and we see that this peak was shifted, in fact, with the same mass as this red puzzle piece, we again theorize that the orange puzzle piece should not be the substructure annotated to the peak because it is not connected to the red puzzle piece. Of course, this doesn't capture rearrangements, which is a possibility, but that's the cost that we have to pay for the current version of ModiFinder. So once that step is done, we find, so that's the annotation step. Once that is done, we find the alignment between the two spectra. And now we can start, sorry, so for the alignment, this again is the same alignment used in GNPS. It's a greedy approximate algorithm. And the way it works is that it tries to find the element that maximizes the cosine similarity score. The main way to do this is to just check all the 2 to the power of p possibilities if p is the number of peaks, but that just takes a long time, and therefore the algorithm used in GNPS tries to approximate this and do it in a greedy fashion, which is faster, but I mean, it's not accurate all the time. So if you're interested, you can read more about this from the GNPS paper. So once this alignment is done, we now have the peaks that are shifted and the peaks that are matched but not shifted. And using that, we are going to calculate the likelihood of each atom being the modification site. So the way it works is for the shifted peaks, we look at the annotations and we see which atoms exist in those substructure annotations, and that is a positive reward. So any substructure in a shifted peak is an indicator that one of the atoms in that substructure is the modification site. And to remove some biases, we use the unshifted peaks as a negative penalty. This is one of the parts. To calculate the scores, and this is essentially the same thing. It's just that we are going to assign these scores as a weighted score. And the way it works is that if a peak has a substructure that has too many atoms, essentially we want those atoms to get less score than a peak that has less atoms because of the amount of information. So this concept is defined as two different scores. One is the contribution score that an atom J is contributing in peak I, and second is the clarity score, and that means how much that peak is distributed over the molecule, because multiple substructures can be assigned to a certain peak. and therefore it can be very ambiguous or very clear. So the combination of these two, clarity score and the contribution score, for the shifted peak as a positive score and the unshifted peak as a negative penalty, is going to give us that likelihood array. This is an example. In this example, let's just look at the peak 56. Here there are two substructure annotations, and it is a shifted peak. So once the scores are calculated, that is the scores that is going to be added as a positive reward to these atoms. And this is the clarity score, which is essentially the weight of this peak. And once this is done, so positive scores for the shifted peaks and negative penalty for the unshifted one, we end up to this final prediction. And the true side is highlighted, which in this specific example, the algorithm is able to find the true modification side perfectly. Okay, so with that done, now I'm going to go through how to use the high throughput ModiFinder. And this is a workflow in GNPS. So if you're interested, you can follow along these steps with me, and hopefully we end up getting to the same results. So once you open your GNPS homepage and log in, then you can click on the launch workflow and search for high throughput ModiFinder. So you can search for high, and you should see the high throughput ModiFinder, and then you can click on launch the workflow. I'm just gonna stop for a few seconds to make sure everyone's following, if they're interested to follow, of course. So once you launch this workflow, choose a name for the workflow, whatever name you like, and then click on this select input data folder to add your inputs. So once you do that, navigate to the datasets workshop ModiFinder and select the selected.mgf file as your input data folder. And select the rest.mgf file as your input library folder. Okay. I'm not sure if I'm going fast or too slow, so please let me know in chat if you need more time. So once that step is done, in the file selection, you should see these two files. So for the input data, you should see the selected, and then for the library, you should see the rest. So because the selected file here was selected from one of the known libraries in GNPS, I removed specifically these compounds from the rest. So when you go to the, when you select these workflow, it always has the whole library of GNPS as the input library. So go ahead and click on the remove file selection for that, so that you end up with just these two files. So selected for the input data and rest for the library. Otherwise, everything is just a direct hit, and like ModiFinder would not be helpful because those are known compounds. All right. So once you have the selected and the rest, make sure to turn on the analog search. So switch it to yes, and then submit your workflow. And then you should see the status to be running, and this could take a while. I'm going to send you a link of one of my own runs, and you can follow the rest from that link while you're waiting for your own to be done. Anyway, you can always find your past tasks from this tasks tab. And once you see this status be done, you can click on the ModiFinder result. So let me just give you one of my own runs for the same input and output. And you can follow the rest of this workshop from that link. Okay, the link is in the chat. Hopefully it works. Let me know if it doesn't work. Okay, so if I'm not getting any messages on the workflow not working, so I'm assuming the link works. So click on the ModiFinder result button right here. So this is essentially the same workflow as the library search. If you have ever used the library search workflow, it is the same. It does the library search for you. And then for the hits, you can go and check the ModiFinder website. So you can run the same library search that as you did before. You can have all the results as before, but also this newly added ModiFinder tab. And once you click on that, you see some data. So one of them is the ModiFinder prediction for the modification side. And another thing that you see is this prediction confidence score. So that says how confident ModiFinder is for this data. So go ahead and sort the result based on this prediction confidence score in a descending order. And hopefully we can start from top and go ahead and try to find our new compounds. So for this example, click on this one, the scan 24429, and then click on view on ModiFinder. So once you sort that, it should be the second one. And then you click on view ModiFinder. Once you do that, it takes you to the ModiFinder website. And you can see on the right the prediction, and on the left a bunch of like different status for this pair. It shows you the number of matched peaks, the number of shifted peaks. So as I mentioned before, we use the shifted peaks and also like the unshifted ones, so the matched peaks. And then the data is mostly carried by the shifted peaks. So if these numbers are considerable, if they're not like 0 and 1, that means the prediction is more trustworthy. And then we have the delta mass. Here it's 84 Daltons, and the type is addition. So the unknown compound has some addition to this one. And we also predict that the addition is of the form of 6 carbons and 12 hydrogens. So that this is the status part. And then these are the different parts that I went through. And then the prediction part gives you numbers, and these numbers essentially are how likely these atoms are to be the modification site. So for this specific example, again, as I mentioned, these are known compounds. I know that the unknown compound has the modification on this part. So ModiFinder is relatively successful in finding the modification site. But let's go through the rest of this website and see what it does. So this part is a mirror spectral alignment. The known compound is always on the top, and then the unknown one is on the bottom. And you can see that the matched peaks are highlighted with blue, and I'm sorry, the matched peaks that are not shifted are highlighted in blue, and matched peaks that are shifted are highlighted in red, and then the unmatched peaks are highlighted in gray, and it's always disabled at first. But if you want to see those peaks, you can click on the unmatched and see the unmatched peaks as well. So now please click on this peak, 76 Daltons. And once you click on that, first it gets highlighted in green, and also the matched one is also shown in green so that you can see exactly what peak it is matched to. And the difference between these two is, of course, the delta between the precursors. And it also shows you what substructure was assigned to that peak. So basically, this is a shifted peak, and this is the substructure that was assigned to that peak. And as you saw earlier, like this means that all these four atoms, they get a positive reward, and their score are increased. Another thing is that you can use this button here to share the link to others. Once you do that, people can access the same data and just look at this. Hopefully this would be helpful when you're working with your collaborators. So let's do another example. So this is one of the examples from the ModiFinder original paper. If you click on this, hopefully it's open example for you, and you click on that and it opens the examples part. So if you click on that and then select this second item here, neptomycin B and neptomycin A. Once you do that, you see that this part, the input part, gets populated with the example. And then once you click on the update button, it should change the prediction to this new input. And here is the first prediction of ModiFinder. For this specific example, because we have the actual unknown compound structure as well, it shows you the modification highlight. So the if you look at the input, you can see the Smiles tool also has something, and that is optional. You can leave that out, and then it won't give you the modification highlight, but it would give you the prediction. So you see that the true modification appears here, and here I've highlighted this like true modification with this arrow. And at first you see that ModiFinder was not able to find the true modification site. One of the parts that it found was very close to the modification site, but it had different sites located with the same score. These two are scored 7, the same as these two, and these are not close to the modification site, and therefore it is not getting a high evaluation score. It's getting 0.5 for the evaluation score, meaning that like the prediction is not that great. And also you see that the possible modification formulas are losing 2 hydrogens and then getting 1 oxygen, or having 1 carbon and 2 hydrogens. However, if you change the ppm to 20 from 40 and increase the accuracy, you can see that it gets updated to 1 carbon and 2 hydrogens. So that's one of the uses of this ppm part. It's also useful for how the spectra are aligned. So if you have a more accurate data acquired in more advanced machines, then you can use a lower ppm and hopefully get a better score. Okay, so for this example, if you could click on the peak 133 and then click, so you see these four substructures are the substructures assigned to that peak when using ModiFinder. But if you click to edit and then remove these substructures, so we are removing these substructures. This is one of the examples explained in the paper as well. But because we suspect that this bond, this amide bond break first, we can hypothesize that this third substructure is probably the substructure that should be assigned to this peak, given these options. And if you go ahead and remove these other three substructures and then click to apply and do that for these other two peaks, 145 Daltons and 147 Daltons, then you see a new updated prediction. Also, these updates happen in real time. So whatever peak you change, you can see the updated prediction. But once you do that, you can see that the two highlighted parts from before are now getting less score, and the true modification site is highlighted with a higher score, and the overall prediction is improved a lot. So this is another part. This is the manual refinement part of the ModiFinder. Of course, because we are using in silico fragmenter tool, we are not using the domain knowledge that a chemist could have. And of course, that is always the best type of knowledge, as it comes from like human knowledge and experience. We wanted to have this ability for you to refine these annotations based on your knowledge. And once you do that, you can see the true modification site prediction to be more accurate. And hopefully this would reduce the time that you would spend annotating all the peaks from scratch yourself and trying to find the intersection of these. All these are now an automated system. So the final thing is that ModiFinder is being actively improved. We are we are developing tools for the modification prediction. So not just the formula, but actual structure of the modification. We are developing algorithms for multi-modification site elements. So one of the drawbacks of the current version of ModiFinder is that it only works on single modification sites. And we do have a tool that predicts whether you have single modification or multiple. And if it's multiple, then it would just show you a message that we suspect this is not a single modification, and the current version of ModiFinder is not able to account for that. But we are developing new algorithms for the multi-modification site alignment. And also we are using deep neural network approaches. So far, what we have is not a deep neural network approach. Everything you saw was a heuristic approach. And so we are doing this deep neural network approach, and hopefully this would change the result for the better. So yeah, ModiFinder is actively being improved. Please, like even if you have examples that doesn't work on the current version, hopefully they would work in soon to come versions of ModiFinder. And thank you for listening, and I'm available for any questions that you have.
All right. Well, thank you so much. So yeah, very nice talk. Very nice to see how we can use this in a high throughput manner. So yeah, with that, we will take any questions from the audience, but first we will allow all of those participants who have to leave. We'll stop the recording and then we will move on for questions.